Hello, this is Fangke from Georgia Tech. I'm going to present our work on detecting MPI usage anomalies via partial program symbolic execution. Message Passing Interface, or MPI, is a widely used parallel programming model. Despite its popularity, MPI programming is known to be error-prone. This is partly due to MPI's APIs not being structured program constructs, which could easily lead to missing synchronizations after non-blocking communication calls. And for applications written in C or C++, pointer aliasing and arithmetic on data buffers for communication can be another source of bugs. And there are also other general difficulties in parallel programming that also exist in MPI programming. In this work, we propose an approach for detecting some of the common bugs in MPI applications. We target at several MPI usage anomalies, which could either be true bugs or uncommon coding styles that may lead to bugs. The first kind is buffer type mismatch, in which the communication buffer's element type is incompatible with the declared data type. The second kind is buffer data risk, which is caused by an access to a communication buffer used by an ongoing non-blocking communication without proper synchronization. The third kind is request overwriting. In MPI, a non-blocking communication API provides a request handle for synchronization using an output parameter. So a request handle can be overwritten by different non-blocking communication calls. If the request handle of an ongoing non-blocking communication is overwritten, the application may not be able to confirm its completion, which is usually undesired. The next anomaly is unmatched wait or test. In MPI, wait and test APIs are used to wait or test for the completion of a non-blocking operation using its request handle. And if a request handle is not initialized by a non-blocking communication API before passed into these wait and test calls, it may result in undefined behaviors. The last kind is unmatched point-to-point or P2P call. It happens when a process issues a point-to-point send operation to another process who doesn't have a matching receive call. We propose to detect those anomalies using symbolic execution. With this approach, we can reason about pointers to communication data buffers in C++ precisely, and potentially we can get better coverage than debugging methods relying on fixed input sets such as testing and dynamic analysis. And for large-scale parallel programs that takes a lot of time and resources to run, we can potentially get better time and space efficiency than dynamically debugging those programs. However, there are several challenges in the application of symbolic execution in a practical MPI debugging tool. They include the modeling of MPI API behaviors as well as the scalability of symbolic execution to large-scale applications. I'll introduce how we try to address these challenges in the rest of this presentation. Here we show an overall architecture of our approach. The MPI application written in C and C++ is first compiled into LVM-IR, on which we perform several static analysis passes to extract some static program information to be used by our MPI anomaly detector. We modify KLEE to support partial program symbolic execution and use it to execute a compiled IR. The MPI anomaly detector, as a plugin to KLEE, intercepts MPI API calls and memory operations to maintain MPI-related states and perform anomaly detection. Moving on to the modeling of MPI, we represent multiple processes with a single process during symbolic execution using a symbolic rank, which serves as a process identifier. In the single program multiple data model that dominates MPI programming, a process uses its ranks to decide the code to execute inside the program. So making the rank a symbolic value can let us represent multiple processes at the same time. When the rank is tested in a condition, we can fork the execution state and let different execution states to represent different groups of processes. The actual message passing is not performed in our model. Instead, we fill the receive buffers with unconstrained symbolic values when the communication is known to be completed. In order to detect anomalies related to non-blocking communication operations, we also record currently unfinished non-blocking operations in an execution state. This is done by intercepting relevant MPI API calls to add or remove non-blocking operation records. Here we show an example to demonstrate how the records are maintained. At the beginning, there's no record in the state. On the third line, the MPI isend call starts a non-blocking communication, so we add a record to the state after the call. On the next line, an MPI test is invoked to test if the non-blocking operation has completed. The result is stored in the flag variable. We fork the execution state into two here. In one state, the flag is set to true and the record is removed. In the other state, the flag is false and we keep the record. Only the second state can enter the if body, where an MPI wait is called to wait until the non-blocking operation is completed. We then remove the record from the state after this call returns. Now we can detect the anomalies. For anomalies related to non-blocking operations, we use the non-blocking operation records in the execution state along with its pass condition to detect anomalies. Specifically, we check if a predefined anomaly condition is satisfiable given the current pass condition and the non-blocking records. For the other two anomalies, we just use pre-computed static information to detect them. Now we discuss how we try to improve the scalability of symbolic execution for debugging large applications. We start from an observation that usually a large portion of the code in an MPI application is not relevant to communication. This means for just debugging MPI API usage anomalies, the time spent in those lines are mostly wasted. To mitigate this problem, we set a limit to both the maximum number of iterations can be executed for a loop, as well as the maximum depth of forks. To further improve the scalability, we also employ partial program symbolic execution. To be specific, we let the users to start an execution from a position in the code they specify, apart from the start of the main function. In our implementation, we allow any function to be the entrance of an execution. A problem with not starting from the main function is that the memory state before entering the entry function is unknown and can have many possibilities. The code shown on the right is an example of this problem. The entry function f takes in a pointer and writes to it. The pointer can point to two different places if f is called from different functions g and h. And during symbolic execution, we need to consider both cases. Inspired by previous work on lazy initialization, we adopt a mechanism that allocates memory lazily at dereferences of symbolic pointers. When multiple memory states are possible at one dereference, we fork the execution to accommodate for them. One notable challenge in this kind of lazy initialization is to ensure the lazy allocation is only done once for a symbolic pointer at its first dereference. In the code shown on the right, we have P and Q loading the same unconstrained symbolic value from a lazily allocated memory block. After Q is lazily initialized at its dereference, we then should make sure P is not initialized again in the return statement. This would need us to check whether the symbolic pointer value has been initialized or not during execution. We use a shadow memory mechanism to achieve it. I'll use the same example to demonstrate how the lazy initialization and the shadow memory work. We have the yellow block representing a pointer-sized memory block. Each memory block has a corresponding shadow memory slot, represented as a gray block. A shadow memory slot stores a reference to a metadata cell. Each metadata cell stores a Boolean value that indicates whether lazy allocation is needed for a symbolic pointer value. And we also have a green block representing a local variable, which also contains a reference to a metadata cell. When entering the function, we have a symbolic pointer m, which needs to be initialized. So m has a reference to a metadata bit of 1. When m is dereferenced, lazy allocation is performed, and we unset the metadata bit m is referring to. When the value of m's first element is loaded into P, the reference to the metadata cell of that value is also copied into P. And we do the same to Q. Note that P and Q are now referring to the same metadata cell because they hold the same symbolic value. Now we dereference Q by performing lazy allocation and unset the metadata bit it is referring to. And finally, when P is dereferenced, because its referring metadata bit is 0, we know it does not need lazy allocation. We evaluated our approach on several benchmarks, including 2 real-world applications, 2 benchmarks from a HPC benchmark suite, a library implemented in MPI, and a benchmark used in previous work. We compared our approach with a static analysis debugging tool called MPI Checker and a dynamic analysis debugging tool called Mask for MPI. The benchmarks contain 13 anomalies in 2 of them. Our approach successfully identified all of them without false positives. MPI Checker raised 3 false positives due to its unsound approximations, and also missed some request overwriting anomalies that it supports. MOST does not support the detection of buffer delays, but it reported all other anomalies successfully. And this table compares the performance of our approach with the other two. Thanks to partial program symbolic execution and later initialization, the time and memory usage of our approach is comparable to the other tools based on static and dynamic analysis. In the other 3 smaller benchmarks, we start the execution from the main function, and the time and memory usage are still in an acceptable range. An exception is the sort benchmark, on which we use less resource, mostly because of the limitation we put on loop iterations. And in conclusion, our approach on MPI usage anomaly detection based on partial program symbolic execution has demonstrated a good precision without incurring excessive overheads. Our code can be accessed through this GitHub link. Thank you.